All right, this is going to be an overview of the Review 3 packet, Designing Studies and Sampling Distribution. So this can be found in Chapter 4 of your textbook and Chapter 7, which also corresponds to Unit 3 and Unit 6, I believe. Remember right. So anyway, let's get started. Observational studies. A sample survey selects a sample from the population of all individuals about which we desire. So we can do surveys. Everybody knows what a survey is, I hope. And your goal is to find out information about a larger population because you cannot typically ask everybody in a population the question. So we do surveys to get that data from it. So there's a few different surveys. We have simple random sample. Let's call that SRS. So that's all possible samples of a given size. So it could be any size. Could be you want to do a sample of size 4. Okay, well, you're not going to get the data with 4, but a simple random sample is any possible sample of that size from a population. We can use technology, a table of random digits, typically, using random number generator or drawn names out of a hat, which suffice. You can do rolling die too. A stratified sample, to get a little bit more less variability in your sample, you can make special ones. So you have stratified sample and a cluster sample. In your random sample, if you want to reduce the variability, you might opt to do one of these two. And let me kind of go over the difference real quick. A stratified sample, a random sample, we do that one first. That's when you have different groups that might have different similar characteristics. So like in a school, you might have freshmen, sophomores, juniors, seniors, and you want to conduct a simple random sample from each of those groups, and then combine data. To get a little bit more representation. So stratified samples and hopefully reduce under coverage. Cluster samples where you have big groups, all right? So maybe like population-wise, and you just kind of section them off or whatever, and you say, all right, I'm going to randomly select this coordinate, this coordinate, this coordinate, and get the simple random samples of those clusters. Everybody in the cluster gets results, and then you compare those numbers in there to get a little bit more heterogeneous groups in the mix. So just different ways. Stratified is more homogeneous, cluster is more heterogeneous, but you still hopefully get good results if you do it correctly. Okay, let's talk about census. Census is just when everybody in the population gets sampled, so nothing really you can do there. You don't have to do any sort of inference for that because you have all the data. With bias, you can get bias a couple different ways. Bias are just like systematic errors in the way that the sampling process has been obtained. So you have voluntary response samples. Those are going to produce bias because it's going to get people that want to answer, right? Internet polls, for example, or mail-in or call-in type things. And then there's convenience samples. Those produce bias because you're only going to get people that are right there. So there's going to be some undercoverage in that as well. So sampling errors can come from random sampling. I mean, there can be random sample errors, but most of the time it's going to be undercoverage, right? Because if you have a voluntary response or convenience sample, you're not going to get everybody that maybe you intended in your population. So those could lead to undercoverage. You can have non-sampling errors too. A few things: non-response, response bias, wording of questions. So non-response just being people cannot be contacted. It's different than response bias. Non-response is like you send out all these questionnaires and you're not getting people to answer. That's non-response. Response bias, when respondents provide incorrect answers. What could lead to incorrect answers? Wording of questions, stating questions in a way that can influence the answers in a certain direction. So if you have terribly worded questions, well, sometimes the goal of a pollster is to have biased results, but the wording of questions can impact the responses you get. It's not going to have to do with the non-response as much, but the response bias can be a direct result of the wording of your question. That takes us to experiments. So those are all observational studies or sampling and just kind of looking at different data. Now, the experimental side is what we're trying to determine if something works or not, right? You have a drug, you want to see, hey, does that drug effective against heart failure or allergy medicine? Is one better than the other? So you do some sort of experiment where you compare the two. The main thing of an experiment is we don't have bias in experiments, we have confounding. And confounding is when you don't know. You don't know what factors led to the experiment to fail or work. They might have some lurking variables in there, like if you don't, let's say you give a heart medicine, and you just do a random sample, volunteers. Well, you might have people in the group that exercise and people that don't. We don't know if that's reducing the heart problems or if the medicine's helping or both. All right, those are lurking variables. So you want to control for those lurking variables. All right, maybe you want to have an exercise regimen coupled with that, or you might want to have people that don't exercise or do exercise, so you don't have that kind of messing up your data. In an experiment, we impose one or more treatments. So a treatment is kind of like it's the thing you're giving to a subject to see if it works or not. The experimental units I like to call subjects. So, I typically say subjects. So experimental units is very formal, but subjects are typically people. Each treatment is a combination of values of the explanatory variable called factors. So each treatment, all right, let's say you have two groups of subjects and each group is getting both treatments, then there could be 4 different factors in that, okay? Each combination of values are the explanatory variables. All right, experimental design, a big thing here. So we want to have 3 different principles that help guide us, okay? For designing an experiment, we have control. How do we control? Do some comparison, okay? There should be 2 or more treatments to avoid confounding the effect of a treatment with other influences, such as lurking variables. If there's only one treatment or one like medicine, then you want to have like things like a placebo or a group that's just even keeled, right? So you can see, oh, what's the difference between people not taking medicine and taking? But you have to have control. There has to be comparison for that control aspect. Okay, so control, comparison. Random assignment is important because we want to kind of, we want to prevent bias and we want to prevent any of those lurking variables in there. So random assignment is going to help prevent that. Okay, random assignment creates treatment groups that are similar, except by chance variation before the treatments are applied. Randomization and comparison together prevent bias or systematic favoritism in experiments. And then finally, replication. Do it enough times so you have good data. Applying each treatment to many experimental units, the higher the end value, the better the results, right? So reduces the role of chance variation and makes the experiment more likely to detect differences in the effects of the treatments. So to repeat, we want to have control. We want to have random assignment. And we want to have key components to a good, well-designed experiment. Different things in an experiment can impact your results. You can have a double-blinded experiment where neither subject nor the experimenter knows what treatment's being imposed on what, or you could have a single blind where it might just be the subject that knows, or it might just be the person running the experiment. So it could be the subject or it could be the experimenters that know, but not both. That would be a double blind if it's both. So both know. You have a fake treatment, a placebo. Placebo effect is when when you are thinking that you're getting the pill or whatever, but when you're really not. Okay, so you have some natural, the body says, hey, I'm going to react this way because I think I'm getting this. That's placebo effect. It's the fake treatment. One of the important things about experiments is blocking. We want to be able to block. If we have experimental groups, gender is a big one, age is a big one, race, different ethnicities or demographics or whatever that might have different reactions to different treatments. It's good practice to block those and then do each treatment within each block to have a better comparison of those data. So we can kind of reduce those that variability between experimental units. And then finally, a match pairs. A match pairs typically is when one subject gets two treatments. So instead of blocking a bunch of people in one block, a match pairs is each person or each subject is the block. And what does that mean? Well, that means that each subject is going to get ideally both treatments, and there'd be a comparison within each one, get the difference or whatever, and then combine your data to get better data, because each person might react differently to the comparison of the different treatments. So matched pairs is each subject is the block. Some experimental designs to think about. Completely randomized design is the most common one. Here's a couple examples we can talk through. So in this example here, you might have 50 volunteer students. They were randomly assigned to one or two groups, 25 each. Each got the one group got one treatment, maybe a coin was flipped. Group one got treatment one, group two got treatment two. It looks like online versus classroom, and compare their SAT scores. So this could be like, hey, getting tutoring for the SAT, either online or classroom, and then comparing the scores and seeing which one gave better results. Or you could have something like this, where you have three different groups, each get a different treatment and make a comparison. But the point is that each, in a completely randomized design, each group gets one treatment. Everybody in that group gets the same treatment, but they are randomly assigned to those groups. So the key thing is our random assignment. Each person in those randomly assigned groups gets that treatment. Now there's block designs where, in this case here, you have many pieces of dirty laundry, light colored clothing, dark colored clothing. In this case here, the colors are the blocks, right? Because there might be some bleeding of colors. And so you want to say, all right, let's get the lights together. Let's see what happens with them in cold water and hot water compare. Let's get the dark colored clothes together. Let's see what happens to those in cold water or hot water and compare. And then overall, we can put our data together if we need to. Or it could be something like 300 volunteer subjects. We have women and men. Women and men tend to form good blocks because they might have different reactions to whatever treatment is being imposed. So you have random assignments, in this case, advertisements, and they want to compare the reaction to the advertisement. So there could legit be different reactions between the women and men. So they want to get those separated, compare the results, and then at the end, we can see what happens. So those are block design. Blocks are important when there's variability between the subjects. And finally, scope of inference. Scope of inference is basically what happens when you do random selection versus random assignment. And I like to use a table like this. When we do a random assignment, we can generally see if there's any cause and effect, all right? So if there's a random assignment, we can have cause and effect determined if we have the data providing that. But if there's random sampling, so if you sample from a larger population, we can generalize to a larger population. But if there's no random sampling, we cannot generalize. If there is no random assignment, you can't do cause and effect. But if you have random sampling, you can still generalize. So if you do a study where you just randomly sample from a larger population, you can still say, all right, I think this is, there seems to be a relationship between this and that, but you can't say this causes that. You understand? Random assignment is what makes cause and effect possible. That's why experiments need random assignment. Observational studies need random sampling to generalize. Ideally, you want both. You want to sample randomly and do random assignment with it. I'll let you read these tips here. Know what's required for a sample to be a simple random sample. If each individual in the population has an equal probability of being chosen for a sample, it doesn't follow that the sample is an SRS. Consider a class of 6 boys and 6 girls. I want to randomly pick a committee of 2 students from this group. I decide to flip a coin. If heads, I'll choose 2 girls from a random process. If tails, I'll choose 2 boys from a random process. Now, each student has an equal probability of being chosen for the committee. However, the 2 students are not a simple random sample of size 2 picked from the members of the class. Why not? Because the selection process does not allow for a committee consisting of 1 boy and 1 girl. They have a simple random sample of size 2 from the class. Each group of 2 students would have to have an equal probability of being chosen as the committee. So the way that random sampling can go doesn't necessarily mean it's going to be a simple random sample. Okay. A simple random sample refers to how you obtain your sample. Random allocation or assignment is what you use in an experiment to assign subjects to treatment groups. They're not synonyms. So random assignment and simple random sample, not the same thing. A couple other things. Well-designed experiments satisfy the principles of control, randomization, and replication. We already kind of talked about that. We want to know the difference between stratifying and blocking. So stratifying goes from surveys. Blocking is for experiment. I mean the same thing, right? But they're in different contexts. Okay, when you're just doing sample surveys, stratification kind of groups them together in different homogeneous groups. When you're doing an experiment, blocking groups them together in different homogeneous groups to compare. And you can pause this and read it on your own. This is kind of more information for you to read through and review. Let's go over sampling distributions. In a sampling distribution, we're trying to get a parameter. Okay, a parameter is the number that describes the population. It could be a mean with the mu symbol, or it could be a p with no hat. Okay, mean, proportion. Those are your 2 common ones. Of course, it could be sigma, it could be the standard deviation. But the whole purpose of a parameter is to describe a population. A statistic would be estimates of those populations. So we do statistics like, hey, what's the statistic for mean? Hey, statistic for mean is going to be X bar. What's the statistic for P? It's going to be P hat. The sigma is going to be S with a little X. Those are your statistics. If you have sample data, you can estimate those parameters using various techniques, but know the difference between parameter and statistic. Okay, a sampling distribution is a combination of a bunch of samples of the same size. Could be means, could be proportions. Sampling distribution could be a bunch of different proportions, p hats, sample proportions. And ultimately, what we're trying to figure out is, hey, do they have, can we estimate the true parameter, true mean, or the true proportion from your sampling, using your sampling distribution? An unbiased estimator is the mean of the sampling distribution is equal to the true value of the parameter. It's an unbiased estimator. The variability of a statistic is described as the spread of the sampling distribution. So when n, larger values give smaller spread. So when n is greater, the spread, aka the standard deviation, is smaller. All right, so for sampling distributions, there's means and there's proportions. These are on your formula sheets as well, but I just kind of have them highlighted here. The mean of the sampling distribution of proportions, sampling distribution of sample proportions is going to be the true population proportion. Okay, so that's given to you on a formula sheet. The standard deviation of the proportion is equal to the population proportion minus 1 minus p. Now 1 minus p is the complement, right? So that's going to be like if p is 90%, 1 minus p would be 10%. And then that's divided by n, all under the square root. So everything gets divided first, and then you take the square root. Make sure you meet the 10% condition. We don't want to have our sample size be 10% or more of the population size. We want that to be independent. So that satisfies independence. So as n increases, the sampling distribution of p hat becomes approximately normal. Remember, the larger the sample size, the more approximately normal it's going to be. And we want to make sure that that normal condition is met. So we want our large counts to be at least 10. So remember, NP has to be at least 10, and N1 minus P has to be at least 10. In other words, your successes and your failures must be at least 10. So we want both of those to be at least 10 to have that approximately normal condition met. With means, again, the mean is an unbiased estimator of the sampling distribution. If a simple random sample size n from the large population has been calculated, the sampling distribution of means, you might have a bunch of sample means. Sampling distribution is approximately normal. I'll stop brown nose there, but the mean of that sampling distribution is equal to the population mean. So that's on your formula sheet. The standard deviation of the sampling distribution is the population standard deviation divided by the square root of n. That's on your formula sheet as well. The 10% condition is not, but we still have to meet that. So remember, n has to be less than or equal to 10% of the overall population, all population. Your sample size must be less than or equal to 10% of your overall population size. So that brings us to, well, how do we get normality? Okay, I kind of skipped over the normal situation here. The central limit theorem. If you have a sample of at least 30, very large sample typically, that means the sampling distribution of your sample mean is approximately normal. So that's called the central limit theorem. You want to know that term. You want to know what it's used for. It basically means you have to have a large sample size, but not so large that it's 10% or more of your population, because then you violate independence rules. So there's kind of wiggle room there. The normal condition, there's a couple ways to get it. If the population distribution is normal, you don't need to have a large sample size. The sampling distribution will be normal. But if it's not normal, this is the key, you have to use the central limit theorem to say that that sampling distribution is going to be normal. So a not normal is going to link to that central limit theorem. We don't need the central limit theorem if you're given that the population distribution is normal, you don't have to worry about central limit theorem. You can have a sample size 10. But if you got skewed data with a large sample, you're good. You got skewed data with a small sample, it's not going to be normal. And that takes care of our sampling and sampling distributions. So now you can try the multiple choice questions, and you can check the video for that, or wait for class to go over. Thank you for watching.